What will happen if the Earth suddenly collides with a huge asteroid? What will happen if the asteroid is 100 to 200 kilometers in diameter? What if there are 2 such asteroids? And what if there are 5? How many of them could there be in total? This question concerns everyone in one way or another. Each of us has thought about this at least once, some in childhood, others at a more mature age. And this question gets a response. Geologists, astronomers, physicists, everyone who is at least somewhat able to calculate the consequences of such a collision, everyone tries to find an answer, and each gives their own. Paleontologists create a theory according to which a 10-kilometer meteorite hitting the area of the Gulf of Mexico and forming the Chicxulub crater would be enough. In their opinion, this would be enough to destroy a good half of all living creatures on Earth, including dinosaurs. Popular science channels like release horror films that vividly show the terrifying results of such a fall. Physicists create online resources where these results are calculated mathematically, and they are not as terrifying as in the horror films. No, of course, it is still a terrible tragedy for a huge number of living beings. But right now we are not talking about specific people, but about the survivability of the Earth in general, its flora and fauna. And in this case, everything is not so frightening anymore. In general, few people realize that the topic of scare tactics, horrors, and the exploitation of fear is one of the most profitable types of business. And that's why media resources will always exaggerate the scale of the problem. So how can we make sense of all this flow of information, what really happened to the Earth, and what could have been and were the outcomes of such collisions? And by the way, where did tectonic plates on Earth even come from? And how do earthquakes and volcanoes work? And what are supervolcanoes really? How did they appear? That's what we'll try to figure out together in this video. Hello, you're on the Age of Skepticism channel with Mikhail Kalmykov, and we're getting started. After the release of the previous video, Defensive Cartography, several questions immediately arose before me, each of which is incredibly interesting in itself and deserves a separate discussion. So where should I start? Which direction should I take my story? I think it's no longer a secret to anyone that denying the impact of several huge asteroids on our planet is simply pointless. The only question is about the dates. For example, on my channel, a film called Catastrophe from the Unnoticed Apocalypse series was released 3 years ago. There, the scenario of the catastrophe is described, and the sizes and trajectories of the fallen asteroids are calculated. And not only in this video, there are at least a dozen such films on my channel alone. And there are plenty of other authors and channels that, one way or another, noticed traces of impacts long before I did. Maybe even a decade ago? I won't list them all, since actually that's almost all the alternative channels, almost all the authors. The one who noticed all this first is probably impossible to find now. And there's no point in that anyway. So let's take a detailed look at the fall of a hypothetical asteroid and try to see the consequences for the planet, and at the same time the mistakes and oversights in the interpretations of various authors. So let's get started. First, let's clarify the initial data. The asteroid is at least 100 kilometers in diameter. Such a giant. Secondly, its composition. It's an ironstone core of an even larger clay asteroid. Thirdly, the entry speed into the atmosphere and the angle of inclination. The speed will be 7 kilometers per second or less, which is important. The angle of inclination is very shallow, from 5 to 15 degrees, no more. Already at this stage, there are significant differences from the commonly accepted versions. The size of the chunk is too large. The speed and angle are much smaller, an order of magnitude less than those of typical meteorites entering the atmosphere. This is not accidental, but I won't explain it yet, because again, there is a whole series of videos on my channel that explains why the parameters are exactly like this and not any different. If this is your first time on my channel, at this point you can either take my word for it, watch the explanatory videos, or angrily close the video. And with an exclamation, "What nonsense is this?" you can unsubscribe. Any of these options is understandable to me. First contact, entry into the atmosphere, and so our asteroid is approaching Earth. The first contact with the dense layers of the atmosphere will occur at an altitude of about 100 kilometers at a minimum angle of inclination of 5 degrees. The distance the asteroid will travel before impact will be about 1,140 kilometers, or maybe even more. That means it won't be as fast as it seems. At a speed of 7 kilometers per second, it will take a whole 162 seconds. That is more than 2.5 minutes. And all this time, there will be contact between the atmosphere and the surface of the asteroid, and of course, its heating. Ordinary meteorites and meteors at this stage simply burn up or explode, but not in our case. Yes, part of the surface, of course, will do just that, but at the same time, it will simply serve as a thermal shield, just like the ones our spacecraft used during landing. By the way, why do meteorites explode in the air in the first place? Here's how classical physics answers this question. When a meteorite bursts into the Earth's atmosphere at tremendous speed, two things happen at once. First, if it's a stony meteorite, air naturally penetrates through its pores inside. Second, the meteorite compresses the air in front of it, and behind it, on the contrary, there is a low-pressure zone. As a result of these two circumstances, the air that has penetrated the meteorite from the front tries to escape from the back and sides, creating a force that tears it apart. But the larger the meteorite, the longer the distance the air has to travel, and the greater the resistance force the stone has to overcome. Therefore, this does not apply to large meteorites, and even more so to asteroids. The same applies to the thermal shield of spacecraft, which have no micro cracks through which air could penetrate. The thermal shield simply burns up in the atmosphere without exploding. And since the speed of complete combustion of a stony asteroid is not that high, by the time it comes into contact with the Earth, it will have burned up and exploded as a result of friction with the atmosphere. At most, only 1 or 2 meters from the surface of the asteroid will be affected, which compared to its total diameter of 100,000 meters is, you have to agree, almost nothing. So after about 2.5 minutes or so, a huge chunk of rock the size of the country of Lebanon or, say, Jamaica, will hit the Earth at a speed of about 7 kilometers per second. Again, the speed won't slow down due to air friction, because the mass of the asteroid is enormous, and the braking effect from friction with the atmosphere in this case is negligible. What works for slowing down small spacecraft is absolutely not suitable for slowing down massive rocks the size of an entire small country. What happens next? A professional and accurate calculation of this is extremely complex, requiring consideration of the terrain and taking into account millions of nuances and details. That's why physicists and science popularizers only calculate the kinetic energy stored in this object, and for comparison, of course, they convert it into the equivalent number of nuclear bombs. This simplifies understanding for the scientist. But to show all this clearly, you need a visualizer. And then an artist, having heard such a description, will start drawing us a picture of a nuclear apocalypse, exactly as he understands it. I'm an artist anyway, so that's how I see it. And the more vivid the artist's imagination runs, the more colorful the picture of the mega explosion he will create. And we, as gullible viewers, look at all this and are horrified. The desired effect is achieved. However, once again, the real picture may be radically different from the artist's depiction. To understand how this will actually happen, let's first use one of the well-known examples that is usually used to visually demonstrate such a collision. For example, a bullet hitting a watermelon or a pumpkin, the poor vegetables fly apart into pieces. And we're supposed to think that the same thing will happen to the Earth. However, this is once again nothing more than a trick, an illusion, a false analogy played out by the artist's vivid imagination, used for the same purpose, to impress and frighten us. After all, frightened viewers buy products better. They're more gullible, more easily controlled. So what's wrong with these simulations? First, the ratio of size and mass. The average watermelon has a diameter of 30 centimeters or 300 millimeters, while the average bullet has a diameter of 1 to 2 centimeters, that is 10 to 20 millimeters. The ratio is 1 to 30 or 1 to 15. This is very important. The coefficient of ratio, because the scalability of the visual model depends on it. But the diameter of the Earth is about 12,700 kilometers, and the diameter of the asteroid is about 100,200 kilometers. So the ratio is completely different. 1 to 127 or 1 to 63. So for the correct ratio, a bullet with a diameter of 2 centimeters and a half millimeter should hit the watermelon. So if we compare it to existing ammunition, it's like a number 7 or 8 pellet, a single pellet, not a whole pack like in a shotgun. Already in this case, we understand that neither the watermelon nor the pumpkin will ever explode. But that's not all. The second misconception is the material that our pellet hits. It's definitely not a watermelon. The material is equal to or exceeds the density of the asteroid. Look, the density of our calculated asteroid is from 1.60 to 2.50 grams per cubic centimeter. The average density of Earth is 5, so it's twice as hard. Well, okay, let's assume that the core of the asteroid is denser, and it can also reach 5 if it's purely rocky, or up to 8 if it's iron, but the density of Earth is exactly the same. The metallic core has a density of about 12.5 grams, and the density of the mantle ranges from 3.6 to 5.6 near the core. That is, in other words, to make the experiment with the watermelon even more accurate, our watermelon should be solid, metallic, at least made of aluminum, but in any case, not made of biomass. Did you notice how the picture perception immediately changes? A metallic pellet hits a metallic watermelon. It's already clear that there won't be any explosion of the watermelon. But this deception doesn't end here. Speed and kinetic energy, yes, the speed and mass of the object are indeed colossal, but to represent their collision to scale, you also need to scale the collision speeds. In experiments, usually a watermelon is shot with a rifle or a pistol, and in this case, the bullet speed will vary from 500 to 1,000 meters per second. But if you scale the collision of an asteroid with Earth to the scale of a bullet hitting a watermelon, then our bullet, the pellet, should be flying at about 10 centimeters per minute. Centimeters. Even a turtle would move faster than our bullet. It's already clear that with such speeds, the Earth definitely won't explode or break apart. In exactly the same way, more serious works manipulate visual perception. For example, the well-known documentary, The Last Day of the Dinosaurs, footage from which has spread to almost all catastrophic videos. They also don't shy away from manipulation. For example, it says that the asteroid fell at an angle of 30 degrees, while at that moment the screen shows an impact angle of 45 degrees or more. In the video, it is said that the asteroid traveled through the atmosphere for about 4 minutes, which is correct. But in the video sequence at that moment, it shows how it covers this distance in 3 or 4 seconds, which is simply impossible. If you calculate the speed shown in the film, it would be off the charts, reaching thousands of kilometers per second. At such speeds, the asteroid would not only leave the solar system and even our galaxy, but even our galaxy cluster. However, of course, the viewer will remember exactly the visuals. The collision itself, which is shown in this film from a great distance, resembles a nuclear explosion magnified thousands of times. Well, I'm an artist, that's how I see it. Actually, the catastrophe will unfold a little differently. Our asteroid will slowly settle onto the granite, and then the basalt crust of the Earth, and begin to press it down. You see, slowly. This, of course, is a relatively scalable concept. Now let's get distracted once again to understand what the crust should have looked like before the collision, and let's recall the previous video, impact mapping in it. At the very end, I said that Earth's tectonic plates are a unique phenomenon that doesn't exist anywhere else in the solar system. That's both true and not true. The thing is, in order to justify their theories, a geologist simply has to find them. They are found with great difficulty, but still, they are found both on Mars and on Venus. But there they are, completely different from those on Earth. Look, let's start with Mars. Here, everything is simple. It doesn't have tectonic plates, its crust is monolithic, but there are faults. It is suggested that they form due to temperature fluctuations on the surface. However, amazingly, all of them run exactly along the places where collisions with a cosmic body occurred. In other words, if there hadn't been collisions, there wouldn't be any faults. Things are a bit different with Venus. It also doesn't have tectonic plates, but there are traces of tectonic activity there. That is, there are lava pools, lava flows, and a huge number of small hills, no more than 100 meters high, which are generally considered to be volcanoes. And there are also solidified sections of lava that have formed raised edges in the landscape, which are generally considered to be plates. However, above all, they most resemble a dried and hardened mud surface. And that's not surprising, because if some time ago the entire surface of Venus was molten magma, then as it cooled, it would logically form just such a surface with narrow rows of raised areas resembling mountains. By the way, that's exactly how mountains look on our ancient maps as well. Most historians consider them to be schematic sketches. Whereas, if you look at Venus, most likely that's exactly how mountain ranges should have looked on almost any planet at the end of its formation after it cooled down. And most likely, these aren't plates as such, but simply areas of uplifted terrain. Plates, in our understanding, moving and interacting with each other, shouldn't exist there, and they don't. The crust of a planet without external influence will inevitably turn into a fairly homogeneous basalt shell, almost a monocrystalline structure. The internal movements of magma in the mantle shouldn't disturb it in any way, let alone break through it, causing volcanism just like in an egg. And by the way, the scale ratios are about the same, a liquid interior and a thin outer shell. But if you poke it with a needle, it will crack and break into separate plates. That's exactly what will happen to our planet if it collides with an asteroid. Part of the enormous kinetic energy stored in the asteroid will go into breaking the Earth's crust, but of course not all of it. At this point, many researchers make another fatal mistake by saying that when the collision happens, the asteroid will bounce off the Earth's crust and start jumping along it, or maybe even fly back into space. No, absolutely not. This can happen with small meteorites, with small spacecraft, with any small bodies, even those 100 meters in size, maybe 200. But if the diameter of the body reaches a kilometer or more, the scenario is completely different. For a body to bounce off, it first has to lose its initial momentum, its initial movement vector, and then receive another, oppositely directed from the atmosphere or the Earth's crust, or simply one directed to the other side. At the same time, all the stored kinetic energy will be transferred to the Earth's surface. But in our case, it's simply impossible. While one part of the asteroid will be in contact with the Earth, the other part will still be in space, and the colossal inertia of the celestial body simply won't have time to dissipate. Therefore, while the upper part of the asteroid will be melting, exploding, turning into dust and plasma, the rear part will continue to push it deeper into the Earth's crust. To push it at a speed of 7 kilometers per second. No explosion, no force will be able to surpass this colossal pressure and speed. A huge ironstone rock will push everything in front of it at a speed 25,000 times faster than the speed of sound. Everything that can explode will be crushed in the front part of the asteroid and turned into plasma. And explosions simply won't be able to happen. It just won't have time. By the time the inertia of the celestial body is dissipated, it will already be quite deep beneath the Earth's crust. On top, it will be pressed down by tens of kilometers of rock, and the monstrous pressure will no longer allow the asteroid to break back out. And again, we see a global difference between how artists visualize it and reality. They draw us colorful explosions, while in reality the picture will resemble the smooth immersion of a hot body into magma. Yes, the kinetic energy of the collision will be colossal, but we shouldn't forget about the pressure, which will increase with every second of immersion. Here again, visualizing the process will be helped by an example with a firearm and a bullet, but this time underwater. A bullet fired, for example, from a Kalashnikov rifle won't even travel 10 meters underwater. And that's all because it doesn't have enough kinetic energy, and water is a rather dense medium that can stop it. Of course, you can increase the bullet's kinetic energy by making it longer and, accordingly, heavier, while maintaining its aerodynamic surface. That's exactly how underwater bullets are designed. They are long and narrow like arrows or darts. However, even this doesn't significantly increase the shooting distance. The maximum is about 40 meters. That is, the pressure of the external environment has a strong braking effect on the projectile. And there's nothing supernatural about that. Our descent vehicles calmly reduce their speed in the atmosphere, and an asteroid will slow down in exactly the same way, but not in the atmosphere, in a denser environment, in the core and magma. Otherwise, everything will be almost the same. Of course, a colossal amount of energy will be released. Part of the rock will turn into plasma, and the asteroid itself will break apart as it moves forward. The Earth's crust at the impact site will be melted, and the crust will crack a little, like an eggshell. The molten part of the crust will, of course, be ejected in splashes for hundreds and thousands of kilometers, forming many smaller craters and plumes. In front of the asteroid, the terrain will crumple, forming mountains or islands. If the impact happens in the ocean, a gigantic tsunami will form, which, however, is still unlikely to be able to circle the entire globe, even if its height is measured in kilometers. The continents will very quickly absorb the energy of such a wave. It is unlikely that it will be able to travel more than 1,000 or 2,000 kilometers over land, although, of course, it will travel much farther over water. And our asteroid, once it gets under the Earth's crust, will stop very quickly. And here an even more interesting process will begin. Well, first of all, it will slightly lift the tectonic plate formed by the impact and shift it a bit, starting the process of this plate floating. This can quite easily explain the discrepancy between territories on ancient maps and modern ones. They were simply shifted entirely, along with all the cities and animals on them. And secondly, do you remember Laren's theory, the hypothesis about the Earth originally being hydrogen? It is based on the idea that a large amount of hydrogen is released from the Earth's interior, primarily from volcanoes. And this is still happening to this day. Based on this, it was concluded that the Earth's core is not metallic, but rather a metal hydride, surrounded by a layer of hydrogen. This hydrogen rises to the surface and passes through the crust, or is released through volcanic processes. This theory did not appear out of nowhere. Many deposits of minerals and hydrocarbons simply cannot appear because there is simply not enough free hydrogen in the composition of magma and the core for such deposits to form. It was necessary to explain where it comes from. However, in my opinion, Laren's hypothesis does not answer two questions. First, how did the metal hydride core itself form? What force made hydrogen combine with metal under such high pressures? Why wasn't all the hydrogen expelled much earlier, even at the stage of Earth's formation, when the process of element separation was taking place? And second, if such a force really existed, then why did it suddenly stop acting and cause hydrogen to separate right now? Nevertheless, Laren's hypothesis at least somehow explained the presence of excess hydrogen in volcanic emissions, and not only there. The formation of hydrocarbon deposits and other useful minerals was previously not entirely clear, since there seemed to be no source for the excess hydrogen, yet it magically appeared. Well, let's try to explain this a little differently. Look, the Earth is made up of various chemical elements. In our case, it doesn't even matter which ones: silicon, oxygen, aluminum, iron, and so on. But let's take, for example, a silicon atom. This is an element from the third period, and that means it has only 3 levels of electron orbitals in its normal state. But there are also excited states, when electrons move from lower orbitals to higher ones. But how and why does this happen? And it's simple. Add energy to the electron and it will move to a higher level. Add more and it will go even higher. How many of these levels can exist in total? Purely theoretically, there can be an infinite number, but in reality, the number of levels is not infinite. In the periodic table of Mendeleev, there are only 7, and not many of them are actually stable. Already after the 5th level, radioactive elements appear, constantly emitting, which want more and more to split apart. The elements of the 7th level live only for seconds, minutes, or even fractions of a second. They are obtained, of course, artificially in laboratories. Why am I telling you this now? Well, here's why. By the time our asteroid entered the Earth's magma, as a result of the rather high speed, 7 kilometers per second, the enormous mass, the huge inertia, and the colossal amount of accumulated kinetic energy, as well as the tremendous pressure, the front zone of the asteroid will not just melt. It will transfer this energy to each of its atoms, to every atom that comes into contact with the Earth's crust. And the electrons of the elements that end up in the way will receive an unimaginable charge of energy and will simply leave their orbits. About the same thing will happen to the nuclei. They will receive a huge charge of energy, lose their stability, and break up into individual protons. A high-energy plasma will form, which sooner or later will begin to cool down. By that time, the bonds between protons and electrons will already have been lost. And the only chemical element that the plasma will then be able to form is hydrogen. There simply won't be enough energy left to synthesize more complex atoms. So the asteroid stops somewhere at a depth of, let's say, 100 kilometers. Although maybe less, most likely even 50 to 70 kilometers, right under the crust. What happens next? Will it blow up the planet from the inside? Of course, artists, excited by analogies about millions of atomic bombs, will draw mega blasts. And what did you expect? I'm an artist. That's how I see it. But no, the Earth won't explode. Of course, the energy of the collision is colossal, but it's not exactly calm around the asteroid right now either. Already at a depth of just 50 kilometers, it will be surrounded by magma with a pressure of 13,000 atmospheres. And the deeper it goes, the greater the pressure. In geometric progression, and at a depth of 1,000 kilometers, the pressure rises to 500,000 atmospheres. Thus, our asteroid will be stopped, and almost all the remaining explosive energy will be sent upward. No, of course, a so-called hydrodynamic shock and seismic shock will pass throughout the planet. However, it won't destroy the Earth itself. Yes, there will be a series of powerful earthquakes. They will destroy cities and infrastructure, but life will not be wiped out. The most interesting things will happen exactly in the place where the asteroid stopped under the Earth's crust. Within a radius of 1 or maybe even 2,000 kilometers, volcanism will begin. Through it, the same kinetic energy accumulated as a result of the collision will be released to the surface. But again, not all the energy will go there. The main part of it will be a superheated cloud that will begin to melt the Earth's crust right above it. Magma will come quite close to the surface and may even spill out. That's exactly how trap regions are formed, which we mistakenly consider to be supervolcanoes. In fact, there are no prerequisites for the Earth's crust within a radius of thousands of kilometers to spontaneously turn into a supervolcano, except for one. A sudden release of a huge mass of superheated magma which melted the crust above it and came close to the surface. No earthly pressure could handle such a number. But a region of magma heated to critical temperatures and left after a collision with an asteroid could handle it perfectly. And at the same time, it also explains a phenomenon like a supervolcano. That's easy to verify. Let's briefly go over the Earth's supervolcanoes. Fortunately, there aren't that many of them, the supervolcanoes of the Earth. There are actually not that many supervolcanoes on Earth, no more than 20, which makes the task of checking much easier and can roughly indicate the number of asteroids that have fallen to Earth. And what's characteristic is that these are mostly the ones that have fallen relatively recently, because over time, the magma will eventually cool down, which is, generally speaking, natural. Out of these 20, to get straight to the point, let's pick the 5 or 6 largest ones. You can check the rest on your own. And could I release a separate video when I have nothing else to do? So, the Aira volcano in Japan and the regular Sakurajima volcano located in its caldera are quite suitable. Look, the Pacific Ocean is a place where several asteroids fell at once, one of which shifted Japan from its place and formed the Philippine Plate. This is how Japan looked on maps of the 16th century, and this is how it looks now. The seafloor relief clearly shows traces of the impact. 2 large grooves run from south to north. This may also indicate that there were 2 fragments that broke apart while still in space. After sinking beneath the Earth's crust, they ended up right under Japan. Not enough, let's move on. Supervolcano, Tuapa region, New Zealand. And again, we see differences between the terrain of New Zealand on old maps and on modern ones. More precisely, on the old maps. Somewhere here is the island of New Guinea. Now it once again has a completely different shape and, most importantly, is once again at the bottom of the ocean. Traces of a massive object rolling over. This time it rolled from north to south and ended up under New Zealand again. Guinea itself, apparently, was simply torn in two, and from the north runs a huge crack stretching for thousands of kilometers, apparently right at the place where the crust was ripped apart. 3 for 3. The supervolcano Toba in Indonesia, on the island of Sumatra, and again at a distance of about 1,000 kilometers from it, we see an underwater trail directed straight towards it, 4 supervolcanoes of Vales, United States of America. That's all here. It's just wonderful. Everything fits, just as it was described in the previous video, a rebound cartography. Shrapnel splashed into the Pacific Ocean again. Of several objects, they were clearly larger in size than the previous ones. On the floor of the Pacific Ocean, there were traces left by the dragging of a slab, and in front of it, an area of crumpled rock had formed, resembling the Cordilleras Mountains. Well, and right beneath them is again our favorite supervolcano 5, roughly in the same place, but a bit higher, there's another supervolcano. By the way, it was this one that shook San Francisco in the 19th century, practically destroying the city. Do I even need to say that the strip at the bottom of the Pacific Ocean goes exactly there? And where would we be without our favorite? Actually, it's located not far from the previous two and could very well have broken off inside the Earth as a more massive part of the same asteroid system. The supervolcano at the Phlegraean Fields is a supervolcano located right under Italy, with its children Vesuvius and Etna situated on either side of it to the south. But how is that possible? After all, nothing fell into the Mediterranean Sea, right? Are you sure? Look at the relief of the seafloor. Exactly the same groove going deep under Italy and Sicily. Look at the maps from the 16th century. Italy is now shifted about 500 kilometers in the direction of this impact, along with Spain, by the way. Well, and where can we go without our Siberian traps? Everything is exactly the same as before. At the North Pole, there is a trace of a huge body submerging, and further along the direction of its submersion, already under the Earth's crust, those very traps formed, supposedly traces of ancient supervolcanoes, which, by the way, were indeed observed there. Among them are outcrops of rocks, the formation of which is impossible without an additional influx of hydrogen, which was noted by the Soviet geologist Larin. Well, as usual, it all sounds wild and unusual. For example, it may raise a lot of questions that the bombardment came from different directions, sometimes from west to east, sometimes from east to west, sometimes from north to south, and sometimes from south to north. And often the bombs could have fallen from opposite directions, almost simultaneously, and for some reason on the same area of the planet, the Pacific Ocean. It's unclear why I use such a small collision speed by cosmic standards as the basis, why such a small angle, and so on. My regular viewers probably remember the video released 3 years ago, and it's called Catastrophe, and it explains this. Then there was a whole series that explained almost every detail in depth. But if you're too lazy to watch my films from the very beginning, I'll briefly explain. First of all, the impact of an asteroid on any planet, not just Earth, is an almost unbelievable event. A gravitational capture is just as unlikely. For it to happen, first of all, the velocities of the asteroid and the planet must match. How and why this happened is explained in detail, for example, in the video Chain Reaction, or in the video series Who Shifted the Earth's Axis. So despite the low probability of such an event, we constantly see examples of gravitational capture. And therefore, I will consider it the most probable scenario, as a result of which the asteroid or asteroids take up an unstable orbit, gradually descending and losing part of their mass, which then smoothly settled onto the Earth as a sandy clay cloud. In the end, the asteroid broke into several parts, and each of them received an impulse in a certain direction, while retaining the general characteristics of the orbit. Thus, they descended almost simultaneously and almost simultaneously entered the Earth's atmosphere. But thanks to the lateral impulse from the breakup, they approached from different directions. Exactly. The same thing, by the way, happens, for example, with the positioning of Elon Musk's satellites. They all have exactly the same orbit, but thanks to the lateral offset, they cover the entire globe with an even grid. So, maybe that's how tectonic plates appeared on Earth, which still bring us a lot of problems with their mysterious movement. By the way, why do they actually move? Why don't they become stable and merge again into a single planetary shell? And that's also the fault of asteroids, but not the ones that hit the Earth, rather the ones that remained in a stable orbit and formed our satellite, the Moon. More about this, again, was discussed a year and a half ago in a separate video. It's actually called the moon. So thanks to the moon, the center of mass of the Earth is shifted and is located at a depth of about 1,700 kilometers beneath the Earth's surface. Thanks to this, the Earth doesn't move around its own axis, but around this center of mass, and this movement kind of wobbles the planet. On the surface, it creates tides, and beneath the surface, it stirs up the magma, and there, too, tidal forces are formed, which also move the plates. It's extremely difficult to calculate such movement because it's unstable and depends a lot, for example, on the phase of the moon, its position relative to the sun, and even the positions of other planets in the solar system. Hello, astrologers. These waves sometimes die down, sometimes intensify, sometimes resonate with each other, amplifying many times over, and thus causing earthquakes and volcanic eruptions. That's almost everything. But there's one more very interesting question. What about the Taklamakan Desert? Something clearly fell there. Something gigantic that formed the Himalayas and the Pamirs, spilled the ancient vast Caspian Sea toward Europe, created Lake Balkhash and Essex-Kul, probably shifted India and reduced the size of the Persian Gulf. Where is its supervolcano? A reasonable question. Let's go point by point. First, in last year's videos, we have determined the date of this asteroid's fall quite accurately. It's approximately the year 1730, give or take 5 years. That is, this is the most recent, the freshest asteroid. Secondly, judging by the scale of the crustal shift it caused, it was one of the largest, quite comparable to those that flattened America and formed it. And what about the shape of the crater? So Lamakan says the angle of impact was quite steep. That means not the usual 5 degrees, but about 15, 20, or even 30 degrees. It went quite deep, penetrating pretty deeply, maybe even 30 degrees. So it's quite reasonable to assume that the overheated, super high temperature magma is still just melting the Earth's crust above it, making its way upward. And most likely the birth of volcanoes created by this asteroid is still ahead of us. But the lightest elements, gases, hydrogen sulfide, radon, just hydrogen, have already reached the Caucasus and the Black Sea. There, a whole underwater hydrogen sulfide sea has formed. And in the Caucasus, geothermal springs rich in radon are bubbling cheerfully and energetically. So it's already obvious which region the magma is rising to. And yes, the earthquake in Turkey is also a consequence of magma breaking its way upward. So in the future, a supervolcano will appear in this region. And if that's the case, this event will allow us to calculate the speed at which magma melts the rock above it, and we can estimate the dates of the collapse of the others. So all the asteroids are actually right beneath our feet in the form of volcanoes and supervolcanoes. Well, almost. But separation by mass and temperature still applies. Naturally, the lightest and hottest gases, mainly hydrogen, started to break through and melt their way to the surface, forming more complex compounds along the way, like air bubbles in water. They rose very quickly and formed compounds like hydrogen sulfide, hydrocarbons, and even water, and that's how gas and oil deposits appeared. And heavier elements, heated to the limit, like silicon and carbon, rise to the surface much more slowly, and this process apparently takes centuries. But even heavier elements, that is metals, can no longer rise to the surface, and after the temperatures even out, they sink to the bottom toward the metallic core, with which they eventually merge into one. That's in theory, but in practice, like at the end of the 1970s. With the help of the then innovative method of deep earth probing, seismic tomography, geophysicists discovered 2 huge and typically located regions at the boundary between the core and the mantle, where the velocities of transverse seismic waves, the so-called S waves or shear waves, were abnormally low. These regions were called. One of these regions is mainly beneath Africa, and the other is in the Pacific Ocean. Scientists are still struggling to explain the mystery of how these regions appeared. One of the leading theories at the moment says that these are the remnants of the former protoplanet Theia, which collided with our Earth and eventually formed the Moon. That is, in other words, even according to official scientists, these are nothing but metallic remnants of another cosmic object that have sunk to the core. The scientists simply combined them all into one and pushed it back 4 billion years in time. To be continued? To be continued. Subtitles created by